can get the talk going. I'm Cody Fox. I'm the executive director of Friends of Alta. I'd like to thank everybody for coming out tonight and supporting our speaker series talk, which is Dust on Snow, How Darker Snow and Faster Melt Impacts Water Resources. Tonight, we're privileged to welcome Dr. McKenzie Skiles. Dr. Skiles is an associate professor in the School of Environment, Society, and Sustainability at the University of Utah, where she directs the Snow Hydrology Research to Operations Laboratory. Dr. Skiles' research methods combine numerical modeling with laboratory analysis and multi-scale observations to understand how much water is held as snow in the mountains and how snow is changing over time. This includes researching the impacts of mineral dust and black carbon deposition on snow in the western United States, where changing snowmelt patterns have important implications for water security. I don't want to take up any more of your time, so please join me in welcoming Dr. McKenzie Skiles.
Thanks, everybody. Okay, I'm going to introduce myself a little bit more in a second, and this was already in the introduction, but in case you're not really sure exactly what a snow hydrologist is, which is what I study, the sort of overarching question is, how much water is held in the mountain snowpack? And that's really important here in the Western US because that's basically where all of our water comes from. But within that really broad field, I'm really particularly interested in when and how fast it will melt, when that becomes available as a water resource downstream, and then how that is changing over time. So it's a pretty niche field of study. There's not very many snow hydrologists. And so I am going to explain how I got into this. I'm going to actually let a recording of myself on a podcast explain. Let's see if this works.
Up in Alaska, I saw changes happening around me that nobody should see happen on a lifetime. Less snow cover, more variability in events, permafrost melting at people's homes sinking into the ground. And I got really interested in climate change. And I wanted to become a climate scientist. And the avenue that took was mapping, looking at trends from satellite data to see, can we see changes? And I, during that time, was also skiing a lot. It's part of the reason why I picked the University of Utah for my undergraduate is the proximity to the mountains. And I probably missed a lot of classes. But I was really interested in the work, and I ended up meeting my graduate advisor. And I told him that I really wanted to study climate impacts on snow. And my first field season, we went out to the San Juan Mountains in southwestern Colorado, which is just a beautiful area of Colorado. And I had skied there before and just fell in love with it. The topography there, there's just jagged peaks, really steep slopes, really amazing backcountry skiing, not that many people. It's pretty remote. And you go out there and you ski and you're basically by yourself. We got to go back multiple times, which is really helpful when you're studying snow because you get to watch it change. And during that season, there was multiple large dust events that deposited on the snowpack, making it darker. Then it'll deposit, it'll get buried again. And then you'll get another dust event, and it'll get buried by more snow. There'll be another dust event, and it'll get buried by more snow. But then when we went back in May, when the snow was melting, all of those dust layers had combined at the surface. And it's the most dramatic thing I've ever seen. This normally bright white snow, what we think of as this bright, clean surface, was red everywhere. It almost looked like soil instead of snow. It was so clear to me then that it was dust controlling the snowmelt timing and not necessarily increases in air temperature. Of course, we have warming, but when you have an impact like this, like dust and we know it's coming from human disturbance, we know it's coming from land use change, you get into this new complexity of it's not just climate change. It's not just warming air temperatures. There's other things going back, feeding back on each other in the system. And I was really hooked. It really hit home how much of our water can come from snow. Like, how could that actually be that we get up to 80% of our water from snow? And when you're up there digging snow pits to the ground and looking at how much snow is actually there, and then looking out all around you and there's snow as far as the eye can see, that's our primary water in the West. And I think at that point, I couldn't go back and study anything else.
So of course, Radio West, if any of you guys are listeners, they do an excellent job. So they did a better job than I usually do at sort of setting up this field of study that I sort of honestly accidentally got into because I met my graduate advisor and he said, I don't understand why you're not studying snow. You miss my class like every other week to go ski. So I said, I don't know why I'm not studying snow either. So, and I kind of just got hooked from there, but I want to step back a little bit and just sort of put changing mountain snow cover in context. So we don't actually have that many observations in the mountains, relatively speaking, but from what we do observe in the mountains, we know that high elevation regions are more vulnerable than lower elevation regions and that they're warming faster. We'd like more observations in the mountains to fill in this record, but across the board, we know that higher elevation regions are warming faster. So what impact does this potentially have on our mountain snow cover? Well, a couple different metrics have been used to sort of look at this. One is this change in April 1 snow water equivalence. That's the amount of water that's held in the snowpack. And if we look across observation sites in multiple decades, we can see that on this sort of standard day that we use to say this is normally when there's the most snow cover on the ground, that over the record, we're getting less snow cover on that day. And that's what those red circles indicate, that there's less snow cover on April 1st over time. There are a few blue circles indicating that there's more, but for the most part, they're red. And then the next plot over is showing change in total snowfall. And again, red is less. And this doesn't necessarily mean less precipitation. What we see with warming air temperatures is precipitation falls as rain rather than snow. And so we're building up less snow cover in the first place. And this is what I want to point out, that warming impacts snow differently during accumulation and melt. So this is actually from the Snowbird Snowtell site in 2023. I picked a dramatic year. And during accumulation, if it's warmer, that precipitation shifts from snow to rain. And then we have variability in the amount of precipitation and when that comes. And, the climate community is still mixed on how strong this signal is, the variability in precipitation amount and timing. But certainly it's happening in some locations. And then during melt, we're building up a shallower snowpack, maybe not in 2023, but we're generally building up a shallower snowpack, and shallower snowpacks are just generally warmer. They're closer to the melting point, and there's less snow there to melt. And then also when air temperatures are warming, we get accelerated aging of snow cover. We're growing our snow grains faster, and that leads to darker snow. And I'll talk about that process more in a second. But really, warming has the biggest impact during accumulation. And there are other processes that dominate snow melt rates. And what's important about sort of looking at snow melt is that if we look at satellite records of snow cover over the Northern Hemisphere, we can see that the anomalies in March, that's that upper plot in green, don't really show any real trends yet. But the anomalies in April, or in June, sorry, in the red plot here, do show a significant negative anomaly towards the end of the record. So we just have less snow cover during this spring-summer transition. So that tells us that snow is definitely melting earlier. So there's something impacting melt. And that could be that we're not building up the same amount of snow in the first place, but it could also have to do with the snow energy balance. And bear with me here because I'm going to explain this plot. Snow energy balance describes all of the various factors that are going to influence both snow accumulation and snow melt. And I'm showing a plot here for just 1 week in May for snow melt. And it's showing the balance of these. If the numbers are negative, that leads to snowpack cooling. If you have mostly negative, your snowpack is going to be cold and accumulate. If the numbers are positive, above 0, that's snowpack warming. You're either bringing your snowpack up to the melting point or you're driving melt. And the different factors that are shown here are long wave radiation. So that's thermal radiation. That's just radiation that's coming in from the atmosphere or being emitted from the Earth. Sensible and latent heat. Those are what we call turbulent fluxes. Sensible heat is what you can think of as air temperature. It's sort of what the air feels like. Latent heat is the heat involved in phase change. So melting or freezing water. And then we have net solar. That's that solid red line. That's the amount of sunlight that's being absorbed by the snowpack. And then if you add all of those up, what you end up with is net flux. That's the energy available to drive snow melt. And we can see that over this week, and of course I picked sort of an idealized week, but over this week, net flux, or the energy available to drive melt, really closely follows net solar radiation. And what that tells us is that it's sunlight that's driving snow melt rates. And it's often conflated with air temperature because as days get longer in the spring and sun angles get higher, air temperature is also increasing. So we often think that it's air temperature that's melting snow and it's actually the sun. And this is just one site in Colorado, but we can look at observation sites across the globe along a latitude gradient from Antarctica to Greenland, and the magnitude will change. Oh, you can't see it, but we can see that net solar radiation, this yellow bar, and some of energy balance terms are net flux, the red bar, dominate the signal everywhere across all observations. So that tells us that it's sun that's melting snow in almost all snow-covered environments. And so then that brings us back to dust on snow and how that plays into sunlight and absorbed sunlight at the snow surface. So I first started studying dust on snow in the Colorado Rockies, and the motivation for that is ultimately just how important of a resource snow is in the Colorado Rockies. It's the headwaters of the Colorado River, which is over 70% snow melt fed, provides water to 7 Western US states and 2 Mexican states. And in remote sensing imagery, what we see is these really obvious large dust plumes that come out of the Four Corners region, primarily the Little Colorado River corridor in Arizona. So it's these large dust plumes. You can see them in remote sensing imagery, and they're basically blowing directly south-southwest and headed up into the southern Colorado Rocky Mountains, or the San Juan subrange, which is the first high elevation point of contact for these southwesterly winds. And as you hit the mountains, that air mass orographically lifts, and as it lifts, that dust kind of falls out onto the snow cover. So this is, you can't really see it that well, but it's dramatic. This is a dust event that happened when I was doing fieldwork in Silverton, Colorado in 2009. And it's like you're on Mars. You can't see that far. Everything is tinted red. And as it sort of clears out, these last anywhere from a few hours to 24 hours, depending on the wind of it that picks up and brings that dust. But it leaves the snow looking like this. And, normally, snow is the brightest natural surface on Earth. It reflects a lot of sunlight. When you make it darker, it reduces the amount of sunlight that it reflects. And so I'll use this diagram to sort of sum up not just the direct impact of dust on snow, but also some indirect impacts of that process. So if you think about incoming sunlight as this number 100%, and you have fresh, clean snow, that snow is going to reflect 90% of that sunlight. That's a lot. That's why you get sunburned when you go skiing. It does get less reflective over time, and that's what we call snow aging. So older snow reflects less sunlight. When you put dust or other dark aerosols on the snow surface, it lowers snow albedo or snow reflectivity in the visible wavelengths, the wavelengths where our eyes see, where there's the most sunlight coming in. It has this really dramatic impact, lowering the amount of sunlight that's reflected and increasing the amount of sunlight that's absorbed. And so that's the direct effect. It's making the surface darker. That additional energy that's absorbed due to the presence of dust accelerates the snow aging process. And that's what we call the grain size feedback. So it's growing those individual snow grains faster than they would in the absence of a darker surface. And that is lowering snow reflectivity in the near infrared wavelengths past where our eyes can see, but it still makes it darker. And so that's a feedback process that's happening. And in that feedback, you're actually melting snow dramatically faster, and you're exposing the underlying ground beneath the snow cover. And that's always darker than snow. And that's called the snow albedo feedback. And it's well recognized in the climate community, because this is why everyone in the climate community is worried about losing snow cover. The more darker substrate or ocean or whatever is getting exposed beneath snow and ice once it melts is always darker and will lead to rapid warming. So there's a couple feedbacks that go along with this snow darkening process. But if we really think about it, it's worth asking, you know, a lot of people think of mineral dust as natural. It's a natural aerosol. There's always arid regions. There's always been desert regions. You know, hasn't it always been around? And if it's sort of a background process, does it matter? Well, we know in the Western US that modern settlement and land use change of the Western US led to dramatic increases in the amount of dust being emitted from the surface. And so the plot that I'm showing here is actually a sediment core from a high alpine lake. And it's oriented slightly weird, but the lower number here, that's before modern settlement of the West. And then it sort of skyrockets up, and that shows sort of this time of modern settlement and widespread grazing of the Western US. And then we see a slight decrease, and that is the enactment of the 1927 Taylor Grazing Act that limited grazing across the Western US. But once you've disturbed the surface, there's kind of no going back. It takes a really, really, really long time for that surface to revive itself, or basically heal itself, so that it's not emitting dust every time the wind blows. So orders of magnitude greater dust, and this tells us that the amount of dust we see today is directly related to human activity and land use change. So how do we actually study what impact this has on the snow? Well, before my time, my graduate advisor got together with some of his colleagues and said, let's actually put out instrumentation in the San Juan Mountains, where it's sort of the front lines for dust on snow deposition. So they picked an area in the San Juan Mountains, Senator Beck Basin, which is right by Red Mountain Pass, in case anyone's been in this area, between Silverton and Uray, and put in 2 towers. This is the Alpine Tower that I'm showing here, and then there's another one below tree line, the subalpine tower. They also put in a stream gauge, and they sort of monitored dust on snow impacts over this whole watershed. So instrumentation went in 2004, and then paired instrumentation, more instrumentation went in at a site to the north of that, Grand Mesa, in 2009 to study spatial variability in these processes. So this is the longest and most detailed record that we have of dust on snow anywhere in the world. Yeah, great question. We are measuring all of those energy balance components that I showed. So we're measuring solar radiation, incoming and outgoing. We're measuring long wave radiation, incoming and outgoing from the snow. We're measuring standard meteorological variables like wind speed, air temperature, relative humidity. We're also measuring snow temperature and soil moisture below into the ground. And there's some specialized solar radiation measurements that allow us to separate out the impacts of dust and snow aging. And in addition to those sort of automated measurements, those are being collected every hour ever since 2004. There's also regular observations, snow pit observations, and collection of dust samples, and also observations of these dust events. And so we know from this record that most of the dust events are happening in the spring. So those happen in March, April, and May. I'm just going to put up a summary slide here. So since observations began, there has been no dust-free seasons. We see dust every year. And most of those dust events are occurring in the spring months of March, April, and May. There's a couple reasons for that. That's when source regions are drying out. And that is also when wind speeds are picking up. The weather is more active in the spring. And the number of dust events is not related to the amount of dust deposited each season. So we can quantify how much dust is actually deposited in the snow as a dust concentration. And what we found from all of those samples over many years is that seasons usually fall into two categories. One is what we call typical. You can think of it almost as a background year, or extreme, where dust concentrations are significantly higher than those typical years. Some other things that we have learned from these sites is that dust is just really, really effective. It's accelerating snowmelt, significantly more so than warming air temperature. So maybe I haven't convinced you yet that it's sun and not air temperatures that are melting snow. But we know this because of our observations, and also because of some dust processes and the way it interacts with the snowpack. So this springtime deposition corresponds to increasing sunlight, day length, and solar angle when the snow is already going to start melting, even if dust is not there. So it's coming at a time when the snow is particularly sensitive. And then dust is not entrained in melts. So as the snowpack starts to melt out and water is flowing through the snowpack and melting out of the bottom, that doesn't actually grab the dust. The dust stays in the layer in which it was deposited. And then all of those dust layers that have been buried sort of over the season combine at the snow surface, compounding that surface darkening. And when we tried to relate back snowmelt rates, how quickly the snow melts, to a number of different factors to understand controls on snowmelt, we found that it didn't exhibit a relationship with these springtime air temperatures or air temperature anomalies. In the presence of dust, it's melting so fast that there's no time over which air temperature to have an impact. And we also did some modeling to say, okay, well, we think it's going to be a lot warmer in the future. What if it's a lot warmer? Does that then have an impact on snow melt rates? And that future climate warming also had a minimal impact on modeled melt rate and timing. It did have a large impact on snow accumulation rates, but not snow melt rates. So we know that dust leads to earlier and more rapid melt, and this has implications downstream. So this reduces water yield and results in snowmelt forecasting errors. So dust on snow darkening advances snowmelt by a month on average in those typical years, but then up by 50 days, so almost 2 months in those extreme dust years. And that is not accounted for in operational forecasting methods. So when we get a big dust year, that leads to errors in operational forecasting from the Colorado Basin River Forecast Center, and those have been directly related to years with high snow darkening impacts. So when you melt snow out earlier, you get earlier green up timing, and those plants are taking up water across the landscape, and so you're shifting evapotranspiration patterns. So that's how much of this meltwater goes up into the air or is taken up by plants. So by shifting evapotranspiration rates, it also reduces snowmelt runoff yield from the upper Colorado River Basin. So I'm hesitant to say that that water is lost because it's going to the watershed, essentially, but it's lost to us as water users. We are getting less water downstream. And that number is actually pretty dramatic. It's about half of the water allocation to the city of LA. So a lot of water. So all of those results that I just showed you, they're all basically from study plots and observations at study plots, sort of these discrete observations through time. And those have been very useful studies for us to understand sort of the basic processes of dust on snow. But ultimately, we're interested in the whole headwaters of the Colorado River. What's going on, not just in the south there, where we know that the snow gets dusty, but what are the impacts across the whole headwaters of the Colorado River Basin, including up in Wyoming and in the Uintas here in Utah, what's going on in those areas? And we can use satellite imagery to quantify this darkening impact. And so that's what I'm showing here. On the left side is just a true color image in 2009. So that's the first year that I started doing field work, when I just got blown away by the amount of dust on snow cover. And the snow like visually looks a little bit dark in this image, but it's hard to tell just how dark. So we developed an algorithm to quantify snow darkening impacts by estimating what clean snow would look like and comparing it to observations of how snow is reflecting sunlight from satellite images that are collected every single day. So we get to see the snow cover base every day. And we can quantify this term called dust on snow radiative forcing. And that's just the additional sunlight that's being absorbed at the dust surface. So not only do we get these cool sort of daily snapshots, but it allows us to study dust impacts in ways that we can't just do from study plots. So I'm going to show a video, and the plot is latitude by elevation. And it's showing dust impacts evolving over a snow melt season. And so we can see where dust sort of shows up at the surface first and how dark that ends up getting, where snow cover stays and where it melts. And we can look at these relationships not only at the daily scale or at the seasonal scale, but we can look over the entire remote sensing record, which for this satellite, which is called MODIS, is 24 years. So we have 24 years daily observations of dust on snow radiative forcing. And all I'm showing here in the middle plot is the median. Over the whole record, that's the median dust impact in the springtime. And then I'm also showing persistence. So how long is dust at the surface actually impacting melt? And what this record tells us is that it's not just the southern Colorado Rockies that are getting impacted by dust. Dust impacts snow everywhere in the Colorado River Basin, but there is a gradient to those impacts. The impacts are highest in the central to southern Colorado Rockies, and they're also highest in the mid-elevation bands. That's basically where snow is held the longest, and it can collect more dust over time. But that means that dust is impacting essentially the largest extent of snow cover that's present in the Colorado River Basin. There's still dust impacts in the Uintas and the Wind River Range, but they're lower magnitude. They're not as dramatic as what we see in the central to southern Rockies. We can integrate across that whole record and look at interannual variability. And this is median dust radiative forcing for every single year and the range of those values every single year. And so we can look at sort of not only the magnitude and range of those values, but trends over time. And one thing we get from this record is that there's really high interannual variability, and we knew that from ground observations. But at the Colorado River scale, the impacts are a little bit more muted than what we see at observation sites. So we can't necessarily say that observation sites are representative of the whole Colorado River Basin. But what we also saw that was a little bit unexpected is that dust impacts were actually more intense in the first decade of this record. So up until 2014, we saw more dust impacts, and then they reduced a little bit, and then they jumped back up again in 2022 and 2023. And we tried to look at a bazillion different factors to try to explain this record, why we might have gotten a decline in dust levels in the most recent sort of decade of this record. And we couldn't find a relationship to anything. We couldn't find a relationship to wind speeds. We couldn't find a relationship to vegetation. We couldn't find a relationship to number of storms, frequency of storms, because usually it's this prefrontal wind ahead of storms that's sort of kicking up this dust. And so we don't know. We don't know why. We can look towards climate modeling as some indicators, and we do know that over the last decade, there's been increased surface roughness, essentially more vegetation in dust source regions, and maybe lower wind speeds, although that's not definitive. And a combination of those two factors might account for this, but we can if we're measuring the wind, but at sort of, mapping scale or regional scale, it's relatively coarse. So it's really hard to accurately resolve wind direction in those records. And so we're working on it, but we don't necessarily know what causes a big dust year versus a lower dust year. And without any clear relationship with sort of these, causality factors, we have limited predictability. So we can't ever say like, oh, we know a big dust season is coming. And that is a challenge because, it kind of catches you by surprise. And the first thing I do when I wake up in the morning is check remote sensing imagery to see if there's dust in there. There's sort of like a group of us that are like dust nerds that like email each other back and forth. You're like, oh, do you see the dust? I don't know. But the satellite imagery then is useful because once a dust event happens and it has an impact on the snow cover, we can see it. We can see it in the satellite imagery. Okay, so that is sort of honestly decades worth of work that I summed up there in those slides. But in 2017, I got hired as faculty at the University of Utah. So I did my undergrad at the University of Utah, and then I left for graduate school, did some other things, and then got hired at the University of Utah. And during when I first started studying dust on snow in Colorado, I was still going to school in Utah, and I was like, man, it would be interesting to also look at it here. Just as sort of like, because I'm here and I ski a lot, like I might as well just collect some snow samples. And so I did. I started collecting snow samples in the Wasatch in 2009. And I was really curious to sort of see like, where would the dust come from here? Because in 2009, I don't know if anyone remembers the Milford Flat fire scar. So that happened in 2008 and just deposited a ton of dust in the Wasatch in 2009. And that's why I sort of started in 2009. For those of you that don't know, the Milford Flat burned, and that's kind of down by Fillmore. And they decided they wanted to plant some seeds, and so they tilled it. And if you till a surface that normally you would do sort of dryland agriculture in, that would be sort of stabilized by plants and roots, once you till it, there's nothing stabilizing the surface anymore, and all the surface soil blew away into the Wasatch. Maybe not all into the Wasatch, but it was a really dusty year. And so that is one of the sort of dust source regions is sort of the severe dry lake bed to the south, or Fillmore around Milford Flat. But also sort of directly to the west of us is the Great Salt Lake Desert. And that is just a huge source of dust. But if you think about these areas, Severe Lake and the Great Salt Lake Desert, these are playas. And so when we get dust in the Wasatch, a lot of it is coming from these dry lake beds that can be either, sort of seasonally covered with some water, or they get wetted down with water. So they're not dust sources all the time. If you make a playa wet, it's not going to emit dust. But once that playa dries out, it can be more available for transport. And there's some things that can happen, like salt crusts, that can help stabilize those surfaces. But sediment is flowing into playas sort of all the time and drying out, and that makes it more available to flow. So we have dust source regions relatively close to the Wasatch Mountains. And so when I started my job in 2017, I said, I've been making measurements here sort of once or twice a year for the last 10 winters or so. I'd like a study plot like we have in Colorado. So I got together with a friend of mine who works for the UDOT Snow Safety Program, and we sort of rehabilitated this study plot called Atwater study plot that had been historically used for avalanche studies, but was kind of just hanging out, not doing anything anymore. So we put instrumentation at Atwater, which is right across the street from Alta, Utah. It's a pretty sweet place to do field work. So this is what Atwater looks like when there's dust at the surface. And this is the dust on snow record that for a long time I was maintaining just sort of out of curiosity. I'd collect some samples at Alta when I was skiing each spring. So in 2009 is when I started these, and also sort of I started observing dust events or having friends observe dust events. So we could reconstruct a similar record in the Wasatch. And you can see 2009 and 2010 at the beginning of that record, they're pretty high. We think that a lot of that dust is from Milford Flat. And then it kind of goes down a little bit. And 2017, that's when we established Atwater Study Plot. And then, you can see 2022 just sort of skyrocketed. And it was the most dust that we had ever seen at Atwater, and the most dust that I honestly had ever seen in the Wasatch, even over that 2009 year. We also saw more frequent dust events. So we had more dust in the snow, and we saw more frequent dust events. And I'll just point out that because in the Wasatch, dust is generally from playas and it's not as iron rich as the Four Corners region does. If you go to Moab or somewhere in southern Utah, you're in red rock country. It's really iron rich, it's really dark, and it's really red. Playa dust around us is more like a yellow brown color. It's not as dark. So that's not to say it doesn't have an impact on snow. Basically anything makes snow darker because snow is so bright. And so it still darkens the snow, but it doesn't visually look quite as dramatic, and it doesn't have as big of a radiative impact. It's not absorbing as much sunlight for the same concentration as the dust that we see in Colorado. And so that just tells you, that source region matters, and dust color really matters. And some characteristics of dust, like particle size, also matter for the impact. Okay, so that record went up to 2022, but I'm going to step back to 2018. Because that was the first time I was up on campus and there was a group of us having a meeting about dust in Colorado. And we looked out the window and we were like, is that dust? And then we all just kind of stood there. And this is from a time-lapse video on the Atmospheric Science Building. But we literally watched dust just come off of the dry lake bed of the Great Salt Lake. We saw the plume start, and then it just blew straight towards us. And I was like, wow, that's like a lot. That's a lot of dust. And I had never really just like been in the middle of a dust event like this in Salt Lake City, Utah. They're actually now, unfortunately, relatively frequent. But I said, I want to study that. I want to see what impact, how much of that ended up in the snow cover. And I know it came from the dry lake bed of the Great Salt Lake, but where else was dust coming from in this event? And so I partnered up with some colleagues in atmospheric science. We did some modeling. And for this one single dust event, so this was April 16th and 17th, or April 13th and 14th. And this date's pretty funny because we almost always have a dust event every year around April 15th. We call it the tax day dust storms. And this one was clockwork, but it was just bigger than the ones that we had seen previously. And so by doing some modeling, we saw, that only 7% of the total sort of dust loaded from this event was from the dry lake bed of the Great Salt Lake. But in this map below, we're sort of mapping these hot spots that are emitting dust from the dry lake bed of the Great Salt Lake, right? So this is leading up to the years where the Great Salt Lake reached a record low level, and there's a lot of exposed lake bed, but only in some areas is that lake bed disturbed. And where that lake bed is disturbed or where it gets a lot of sediment load, those are the hotspot dust source regions. And the reason why it's such an important dust source is because it's right next door. It's so close to us. that dust does not have to travel that far to get onto our snowpack. It's on the scale of sort of like tens of miles, as opposed to in Colorado, we're talking about, sort of hundreds of miles that the dust is traveling. So it's so close, and it hits right up against the Wasatch that almost inevitably all that dust that's getting blown is getting deposited into the mountains. And that's why it makes it such an important dust source region, not because it is all of the dust is coming from the dry lake bed, but because it's so close to us. And so studying this one single dust event in 2018, we saw that dust was accelerating snowmelt by 5 days on average. So that's a week. And that's relevant because that's one dust event. So then I was like, I need a graduate student to study this. And so my PhD student, Otto Lang, started. And then he just finished his PhD actually, but he did his whole PhD on dust in the Wasatch. And so this was his first paper. And he took all these observations of dust on snow over an entire season, and then was able to model the impact of dust over the entire season, not just one event, in 2022. So that was this big dust year. And then we were able to look at, dust source regions over the entire season, not just for one event. And then we found that the Great Salt Lake dry lake bed was counting for almost a quarter of the dust in 2022. And this was when it was at its maximum low level. So there was more exposed dry lake bed. And basically every wind event, our storms come in from the west, sometimes from the northwest, but basically every wind event is going to pick up dust from the dry lake bed and deposit it in the Wasatch.
What's the GSL?
That's the desert. That's the Great Salt Lake Desert. Yeah, good question.
So that's exposed area regardless of water level?
Yeah, it sometimes gets saturated with water at times, and then it won't emit dust, but it's basically it's a pretty constant dust emitter, that Great Salt Lake Desert.
For this study that was done in 2022, when you were showing that plot earlier, kind of the annual route from like 2009 till 2022 to the big spike, was this data or collection over the whole season included in that?
Yes, yeah, good question. Yep, all the dust samples that we collected at Atwater, this is all for Atwater study plot, was included in that. That's what makes up that 2022 year.
Yeah, I guess it makes me curious about like the sample size collected at each year, just to see how that would contribute.
Yeah, it could be due in part to us just getting better at observations and more frequent observations. Yes, excellent point.
Every year you're collecting full profile.
Every year we wait prior to 2017 and in previous years, because dust doesn't get pulled through with meltwater, I would just wait until all those dust layers were at the surface and then collect a sample. So we call it like end of year dust. And that's the same thing in 2022, but we knew exactly when that happened because we were watching the snow really closely. Okay, so it advanced snowmelt by 17 days. So on the scale of a week to a couple weeks is our current estimate of the impact of dust on snow in the Wasatch. And it doesn't sound as dramatic as what we see in the Rockies. But I think this next slide will help highlight how important snow is in the Wasatch. The Wasatch is a knife range. It sort of dominates our, skyline, but it's a tiny mountain range. It's not very big. It's like very narrow, very skinny, but that's all of our water. Salt Lake City would not exist without the Wasatch. We live in a desert, and without the snow melt and without sort of predictable snow melt timing, we don't have much reservoir storage in the Wasatch like we do in other parts of the Western US. We have some, but a lot of times when the snow is melting, that's dictating when water is available for use. And so we want to be able to understand what's controlling that snow melt timing. But there's also sort of an economic impact here, right? The snow sports economy is huge in the Wasatch, and nobody likes to ski on dirty snow. And so when the dust comes, and not only makes the snow less fun to ski, but also looks less appealing, that matters. And it's melting the snow faster. Probably has the biggest impact on a ski resort like Snowbird that can stay open for later, but it's relevant. These impacts are relevant. And so we can also look at the satellite record in the Wasatch, which is a little bit harder to see because it's such a skinny range. But we did this we looked at all of the headwaters for the Great Salt Lake. So that's the Bear, the Weber, and the Jordan Provo. And we looked at them separately to see if there were differing dust impacts from north to south. And over the last 24 years of the satellite record, could dust on snow or accelerated snowmelt be playing a role in the declining lake levels of the Great Salt Lake? And I'll just kind of ruin the story now. We didn't see that. We didn't see a dramatic impact of accelerated melt that could contribute to less surface runoff to the Great Salt Lake. So we as humans using more water, we're responsible for the declining lake levels of the Great Salt Lake. Some of the takeaways from this work is that in contrast to the Rockies, the dust on snow impacts were relatively consistent across all three headwater basins. So we didn't see a gradient from north to south or south to north or east to west. We didn't really see a gradient. And so that just means that we think the dust sources are relatively close and all of the snow cover gets sort of equally covered by dust each season. If we look over the full record, just like we did in Colorado, we do see a lot of variability. In 2022 and 2023, even though it was a big impact at Atwater study plot, we didn't see that pop out in sort of the whole headwaters record. We did see 2008 and 2009 pop out as a relatively high dust impact year. And then also 2014, which I don't know what was happening in 2014. I don't really know why that was a high dust impact year. We don't understand exactly what's controlling these patterns. Or why even in the Wasatch, we've had sort of this more muted dust impact over the more recent decade. But unlike in the Rockies, here in the Wasatch, there's no statistically significant trend over the remote sensing record. So it's hard to draw much conclusions from this record, other than the fact that there's dust present every year. There's a lot of interannual variability, and we still don't really fully understand what determines a big versus low dust on snow year. Okay, so I am gonna skip through some of this because I want to leave time for questions, and we're sort of running up against the end of the hour. But I just want to point out, why does this all matter? We know dust makes a big impact on snowmelt rates, so it's worth asking the question: can we actually account for dust impacts in snowmelt forecasting to improve hydrologic prediction? And I'm going to skip ahead to how we do snow forecasting right to this. Currently, if you don't know, we operationally forecast snowmelt two different ways in the Western US. We do statistical stream flow forecast, which relates winter and spring snow water equivalent, so the amount of water that's held in the snowpack, to spring and summer stream flow. So this is a statistical relationship developed over multiple decades. Or the Colorado Basin River Forecast Center does a temperature index runoff forecast. It's also a calibrated relationship over multiple decades, but it's calibrated between runoff, air temperature, precipitation, and snowmelt. So these are all, sort of assuming the future will be like the past. And variation from the calibration period conditions will result in forecast errors. And so our goal is to be able to sort of represent the physical processes that control snowmelt. And we're never, at least not in the near future, moving away from this sort of calibrated approach. But, we do want to help these operational forecasters sort of move past this assumption that the future will be like the past. It's sort of built in, it's really hardwired into our forecasting frameworks right now. But we're trying to nudge them or push them towards process-based modeling informed by observations. And, up until recently in the last few weeks, I would have said we're making leaps and bounds in numerical weather forecasting that allows us to drive these models, these process-based models, and also remote sensing. We can use satellite records to inform and update these models. And so these are real-time observation of snow-covered area and snow albedo that we can put into spatially distributed models to actually tell the model what's happening with snow albedo. And this accounts for the impacts of dust. So we have these data sets available we can put them into a snowmelt model that accounts for all of those energy balance factors that I showed you a plot earlier. And I'm going to skip through this, and we can run the model. We can build up and melt out a snowpack across an entire landscape, and not rely on any sort of historical data to inform that. We're forcing it with observations, with real-time observations, and also with weather forecasting data. And so additionally, I mean, it's not just a pretty picture, but in this one, I'm showing the energy balance. So if it's green and the arrow is up, that means more energy is going out of the snowpack, allowing the snow cover to accumulate. And so we're building up the snowpack. And then the arrows, once they turn orange and start pointing into the snow cover, that is when there's more energy sort of going into and forcing snowmelt. We're bringing snow up to 0 degrees C and forcing snowmelt over time. So at every single sort of grid cell in this model, we know exactly what's happening with the snow cover. And we can run these models across, headwater basins in near real time. This isn't sort of a historical model. And so by informing a snowmelt model with snow albedo and dust on snow impacts from satellite data, we can model timing and magnitude of dust impacted melt. And we are working with the Colorado Basin River Forecast Center to integrate this type of modeling into their forecasting framework. So I kind of ended here on, we still have a lot of work. We still have a lot of work to do. There's some opportunities and some gaps. We want to model dust on snow impacts at watershed scales and implement this sort of operational forecast modeling over, every snow dominated basin in the Western US. We want to incorporate that into the CBRFC, the Colorado Basin River Forecast Framework. And then what we're working towards is sort of ensemble forecast runs for possible range of dust conditions, because we can't predict if it's a big dust year. We can say, well, we think if it's going to be a big dust year, snow will melt like this, or if it's a low dust year, snow will melt like this. We can do these runs sort of scenarios forward in time. And then dust prediction. There's a lot of work still needed for us to be able to say, well, even a week out, like, do we think a dust event is likely or possible? So a lot of work is left to be done to what drives variability at interannual to decadal scales. And then in a given season, can we predict what dust on snow impacts will be, incorporate that into hydrologic modeling? And then mitigation. This is tough because land use change is such a distributed problem coming from so many different sectors that it's hard to control. And once you break a crust, a biological or physical crust in a dust source region, it can take decades for it to come back. And so once you create a dust source region, that dust source region is persistent. And so, there are ways to mitigate dust, but that would take a lot of policy solutions. And so we hope that will happen, but we're not there yet. I just want to recognize, I'll close here and want to recognize my lab group, the Snow Hydrology Research to Operations Lab. Once you get to my career stage, it's the students that are doing most of the work. And so a lot of the work that I presented today are from a couple of graduate students in the group, PhD students, Pat Naple and Otto Ling. And then I will end there. Yes.
So this is like all of the information that you presented here was related to the Colorado River Basin or more locally, right? And is this happening in other places on the planet that are snowpack driven systems that feed socioeconomic systems, like in Asia, in Europe, in South America, and is there a group of cohort of people that are building for long-term collaborative, like, meta-analyses of what this might look like if we combine those?
Yeah, that's a great question. I actually cut that slide. I had a global perspective slide where, yes, we do know there are other places where not just dust, but also other dark aerosols like soot, black carbon, brown carbon, just other aerosols are darkening the snow cover and accelerating melt. So that includes like the Himalayas and high mountain Asia. That includes the Alps. The Alps get, if you've ever seen these pictures, there's always someone skiing on this like bright orange dust. There's always these dramatic pictures from the Alps. And other smaller ranges too will get episodic dust events. It's very common for snow in the mid latitudes. And then in China, there's also snow cover that's really sensitive to black carbon deposition, really high concentrations of black carbon. And so, you know, there is a group of academics or scholars that sort of study it in these different regions. We could probably be better connected. But we did get together a few years ago and wrote sort of a review paper of like what we know now. And so I'm sure that in another 5 or 10 years, we'll do that again and say like, has anything changed? And I know that we're all working, you know, it's different because sometimes it's, you know, in the Alps, a lot of the dust is coming from the Sahara. And so dust doesn't know any sort of like regional boundaries. And so it's not always that you get to go, like I get to go and talk to farmers who are trying to mitigate dust. But it's a little bit harder to do that when the dust is coming from the Sahara. Yeah.
Yeah, great talk.
Yeah, thank you.
I have 2 questions. My first one relates to what she was asking, and that is if we look at not just snowpack, but persistent snow and like a glacial scenario, I assume that these effects are persistent, right? It's not
Yes.
just annual.
Yeah.
So if you can talk a little bit about that, if that's in your area of expertise. And the second one is biological, like if we end up with small dust amounts but high nutrient level, we also end up with biological factor like algal growth. And what is that?
Oh, you guys are well prepared. These are good questions. Okay, so for glaciers, yeah, so I sort of focus or specialize on seasonal snow, but I've done research on light absorbing particles all over the globe, including Greenland and Antarctica and glaciers in Alaska, and in Washington. And what we can do on glaciers, actually, it's a very nice sort of record keeper for aerosols. You can core down into the ice and actually get these layers from multiple years back and reconstruct what concentrations were over time. But, you know, at the toe of a glacier or of an ice sheet, previously, it's the same thing as snow cover. Previously deposited layers will come to the surface. And that way they kind of conglomerate into these like melt channels, and you get these really dark melt channels. This is actually contributing to the declining sort of albedo and faster melt on the edge of the Greenland ice sheet. But that's like really ancient dust that's coming back up to the surface. But what glaciers have an impact that seasonal snow doesn't have is that fires in the summer can emit stuff and deposit stuff on perennial snow cover and glaciers and make the surface darker in the summertime. Seasonal snow, at least for now, tends to be offset from the fire season, so we don't get much deposition of aerosols from fires, but that does impact glaciers. And then for algae growth, that is, you hit the nail on the head. Dust is nutrients. And what you need to grow algae, have any of you guys seen like watermelon snow or like red snow cover? That's algae growth. And that happens when you meet sort of 2 demands. It needs water and it needs nutrients. And so usually the algae will bloom in late, like really right before snow melts out. And so it does have an impact. Seasonal snow, it tends to have a minimal impact because that's blooming like right before the snow actually melts out. So it's only impacting snow for a little bit of time. That's very important in perennial snow cover because it can stay on this sort of perennial snow cover for longer amounts of time, lowering albedo and having a larger impact. So it is important in glaciated areas where snow cover sticks around year round.
So you said like the Wasatch being a 9-foot ridge. How much does that, because you said you analyzed the north and south effects of dust on snow. How much did you factor in like the distribution of dust further east and like the Uintas and stuff like that? Like how much does dust play a role in those snowpacks?
Yeah. So the Uintas are in, they melt out to the Colorado River. So we've actually spent a lot of time looking at the Uintas. And they're a very interesting area because just adjacent to the Uintas, there's a lot of oil and gas development. And so what we have seen in the Uintas is that you do tend to get dust. It's the same sort of color as what we see here. It's sort of like lighter colored dust. And it tends to have an interesting spatial pattern. It tends to be sort of on the south slope of the Uintas. And we have actually seen that's the only area that we saw declining dust impacts in the Wasatch. So not the Wasatch front, but sort of the Wasatch back and into the Uintas. We saw some declining dust levels. And we don't know for sure if that is actually related to oil and gas development, but that's the current hypothesis, is that dust levels in that region are somehow related to oil and gas development or building roads out there. Yeah.
Because those oil fields are now a little bit older.
Yeah, that's, I'm not an oil and gas expert, but yeah, we think that the development happened early on, the disturbance happened earlier on, and there hasn't been a lot of new roads being built recently. Yeah.
Just wanted to add that kind of your question. I think you still go to AGU, or American Geophysical Union conference, once a year, which is the largest, there's other conferences obviously, but this is the largest one where they get together. They have full prize for people from that study glaciers and snow. They get together. That's like a great opportunity. I know traveling and funds and stuff been difficult, but when I used to go to those conferences, it was really good because then everyone gets together, and that was the best part, to network across the different researchers, different areas around the world doing those kind of studies.
Yeah, so yeah, we that's usually where we get together and chat and see what other people are working on, if we can learn from other parts of the world, sort of how they're studying it, and what methods they're using to sort of observe these impacts.
Could you tell us anything about what's inner dust, our specific magic dust that was that?
Yeah, great question. I don't necessarily study the composition of the dust, but I have colleagues that do. Greg Carling at BYU has collected, and I've also given him dust on snow samples to look for heavy metals. And we do see sort of trace heavy metals in the dust. It's the same that we see in dust collected from the dry lake bed. And none of those levels currently exceed sort of concern levels, but we do know that heavy metals that they sort of collect in the dry lake bed, or they collect in the sediment in the lake, and then when it dries out, there's heavy metals that then can get picked up and deposited. So Greg has looked at the dust in the snow, and then also the snow melt in the streams, and he does find tracers of that, but nothing that has yet brought us up to a level of concern that it's contaminating our drinking water.
Is that also how you classify where the dust is from then?
We can, yes, that's one method that we can classify where the dust is from. We actually use sort of isotopic signatures, and those isotopic signatures vary by different dust sources. And so it's not like a fine, we know exactly it came from this spot, but it can tell us generally if we've collected dust samples from those source regions. It allows us to fingerprint it back to what has been contributing to the dust on snow. Paul.
Given that snow is so important to the western US and areas like it all around the globe, why do you think there are relatively few snow hydrologists?
Great question. Yep.
I don't know, Paul, you've been doing this for longer than I have. What do you think? There's relatively few.
We're academic cousins. Even though I'm 20 years older than you. Our advisors both work out of the same lab, out of Jeff. So there are not very many people that do this. I think people take it for granted that it gets warm and snow melts, and it's pretty easy, and what fall stays there.
I really skipped over some stuff here, but I was just going to show. Have you guys heard of the SNOTEL network? That's that's how we observe snow cover in the Western US. It's really unique to the Western US actually to have this sort of dense network of snow water equivalent stations. And I think that this might actually have something to do with it, because we put in some, there was a couple real smart water people that were we know it's coming from snow, And we're going to put out observation sites all over the place. And we're just going to use those and relate stream flow to measurements at those sites. But you can see in these plots that it's showing the distribution of where those actually are. And those sites, they were placed in areas that keep snow for the longest so that these relationships could be developed. It's north-facing sort of open areas below tree line, and we miss the highest and lowest elevations across this network. So it's not a climate network, it's a hydrology network. But I think this has something to do because everyone's like, oh, we have so many observations of snow cover. That's great, that's a great data set. The work's done for us, but it turns out that it's not actually the case.
So when I get questions like that, I say you could fit all of those individual dots within the football field. Each snowtail site is 4 square meters. You know,
Yes, but we're grateful that we have.
So.
But we're grateful that we have them.
Great. Like, who can make sense of what's happening in that area that's larger than 4 square meters.
I will say that, you know, having worked with operational forecasters now, like really kind of hand in hand for the last like 5 or 6 years or so, we've been looking at their errors and we're pretty good. We're pretty good at forecasting snowmelt, it turns out still. But, you know, we all know it's coming. There's gonna come a time, either due to funding cuts or climate change, where forecasts are not as good. And all the research that us few snow hydrologists have been doing after this time is going to become really valuable. And we're trying to help them transition into these new sort of more modern methods before that time frame really hits in earnest.
Incredibly valuable. Incredibly valuable.
Thank you. Yeah.
So,
This is less of a.
It's true. It's true in the current political climate. I mean,
Yeah.
thank you. Like this
No,
has
you're
to be
welcome.
done. There has to be continued effort.
Yeah. I didn't know what I was getting myself into when I first started doing this, but now it's like, it's kind of, you know, it's like you get into something like this and it turns into your like life's work. So it's important. It's important to me. Yeah.
Solid.
Victoria, do you want to say something?
Yeah. This is not necessarily a question, but I guess future work studying in Utah specifically, it would be, because I know there's been a lot of development and actually increase of population and people like in buildings and I know as you just meant as well. I'm kind of curious on those correlations with the human population factor as well from like different spots.
Yeah, I mean, we know that dust is related to land use change. And we know that land use change is caused by humans, and we know that humans are not going away. Populations in the West are sort of exploding. And so this is a sort of, there's feedbacks there too. There's more people, there's more dust, there's more people that need water. We know that our water might become less reliable in the future, and that's a big problem for all the people that are living in the Western US. So there's sort of these relationships here that we don't know how they're all going to play out. But yeah, I mean, I think, you know, we can think about dust mitigation, but I also like to think about, you know, getting the word out and just helping people think about sort of surface disturbance and being gentle. And there's a lot of people doing, so, you know, arid land scientists and soil scientists that do a great job on this. It's like, they're the don't bust the crust people, like when you go down to Southern Utah. And dust has so many impacts, you know, for our health, for visibility, for crop health, for so many things. So there's a lot of people that are really concerned about dust. There's a few of us that are really concerned about dust on snow. So we do have a broader network of sort of dust folks that work together on these topics. Yeah. Okay. I think I've kept you guys long enough. Thank you for coming.